Welcome to the Explainer. Large language models, they really do feel like magic, don't they? They can write poetry, they can write code, but what if I told you that this entire incredible technology, from simple chatbots to complex AI agents, is all built on one surprisingly simple idea? So today, we're going to unpack that core principle and see exactly what makes these powerful systems tick. I know, it sounds almost too simple, right? But seriously, don't let that fool you. That single sentence, it is the absolute foundation. I mean, everything an LLM does, no matter how complex or even kind of weird it seems, it all comes back to this one core function, just predicting what comes next. It really is the key that unlocks the whole thing. Okay, so here's our game plan. We're going to start with that core prediction idea, then we'll peek under the hood at the actual architecture that makes it all possible. After that, we'll look at how these models are trained and then see how they're evolving into these proactive AI agents. And finally, we'll check out the big players in the game right now and tackle some of the huge challenges they're facing. So if it's all about just predicting the next word, how does a machine actually learn to do that? Well, it all starts with translation. The machine has to turn our world, the world of language, into its world, which is the world of numbers. You know, at the end of the day, an LLM is just a massive pattern recognition engine. It's consumed a huge chunk of the public internet, books, articles, you name it. But here's the thing, it's not understanding language the way you and I do. Instead, what it's doing is learning the statistical chances, the probability of how words and ideas connect to each other. And it's doing this on a scale that's honestly hard to wrap your head around. And this right here is that crucial translation step I mentioned. So the word running doesn't just go into the machine as running. First, it gets broken down into something called a token. Then that token is turned into this long string of numbers. That's the vector. Think of that vector like a coordinate on a gigantic, multi-dimensional map of meaning. And that's how the machine knows mathematically that the coordinate for running is super close to jogging, but way, way out there from something like photosynthesis. Okay, so we've got our numbers. Now let's talk about the engine that actually processes all of them. This is where the real magic happens. You know, before 2017, the big problem was context. Older models would basically forget the beginning of a long sentence by the time they got to the end. But then the transformer architecture came along and it changed everything. It gave these models a new superpower, the ability to look at an entire chunk of text all at once and, this is the key part, to pay attention to which words are the most important to each other, no matter how far apart they are in a sentence. Okay, I know this looks super complicated, but let's just focus on the main idea here. You see the input over on the left? It flows through all these repeating blocks, and inside those blocks is the secret sauce, something called multi-head attention. This is the mechanism that lets the model read a sentence like, I went to the bank of the river, and figure out that bank is connected to river, not a financial institution. It's constantly making these little connection calculations, and the results get stored in its billions of parameters. You can think of those as all the tiny little knobs and dials that get fine-tuned during the training process.
Right, so having this incredible engine is great, but it's not enough. It needs fuel, tons of data, and it needs, well, a driver's ed class. And that all happens through this really thought-out, multi-stage training process.
It basically happens in three big stages. First up is pretraining. This is where the model just slurps up a huge chunk of the internet. It's learning grammar, facts, a bit of reasoning. Then comes instruction tuning. Here we teach it the Q&A format, you know, how to be a helpful assistant. And last, but maybe most importantly, is alignment. This is where real humans actually rate its answers. It's a technique you might have heard of called RLHF, or reinforcement learning from human feedback. This is what teaches it to be not just correct, but also helpful and, safe. And this slide just perfectly shows that transformation. The base model, that's like a genius librarian who's read every book in the world, but is kind of scattered. It knows everything, but you can't really ask it a straight question. But the tuned model, that's the same librarian after some customer service training. Now they're a helpful conversationalist who actually understands what you need. But okay, the evolution doesn't just stop there at being a good conversationalist. The latest big leap is turning these models from just passive text generators into active, problem-solving agents. And this is a really profound shift. You know, that basic next word prediction, that's kind of like our brain's system one thinking. It's fast, it's intuitive, it's automatic. But what we're seeing now with AI agents is the development of a system two. When you give them a complex goal, they can actually pause, think, create a step-by-step plan,
figure out what tools they need, like a search engine or a calculator, and then go execute that plan. And this ability to use tools, it solves one of the biggest drawbacks of LLMs, the fact that their knowledge is basically stuck in the past, frozen at the time they were trained. This whole process has a name, Retrieval-Augmented Generation, or just RAG for short. The idea is simple. It retrieves up-to-the-minute information from the outside world and then augments its own knowledge to give you an answer that's actually current and fact-checked. This is a fantastic example of that in action. So a user asks the agent a pretty complex question, describe this picture and count the stuff in it. So what does it do? It doesn't try to do it all itself. First, it makes a plan. Then it goes out and finds other, more specialized AI models, one that's great at describing images, another that's good at spotting objects. It runs both of those, gets the results back, and then puts it all together into one single coherent answer. It's basically acting like a project manager for a team of other AIs. It's incredible. So with this massive explosion in what these things can do, it's no surprise that it's kicked off a fierce competition and a really, really important debate about who gets to build and ultimately control this technology.
You know, for a while there, it seemed like the best, most powerful models were all locked up inside a handful of huge tech companies. But wow, the open source community has been catching up at an absolutely staggering pace. And that's created this really interesting choice for developers. Do you use a simple pay-per-use API from one of the big guys? Or do you download a powerful open source model and get all the freedom to run it, tweak it, and completely control it yourself?
And yeah, this table gives you a quick snapshot of the big players. On one side, you've got the closed proprietary models from companies like OpenAI and Anthropic. Super powerful, super easy to use. And on the other side, you've got these open source titans from places like Meta and NVIDIA. These are the models that are fueling this huge wave of innovation happening everywhere else, because developers can get their hands on them directly. But of course, as these models get more and more powerful and as they get woven into the very fabric of our lives, we're starting to run headfirst into some really big problems. So how can we be so sure these models are going to keep getting better? Well, the answer is in something called scaling laws. It's a pretty wild discovery. Researchers found that with almost spooky accuracy, if you just keep throwing more data and more computing power at these models, their performance gets predictably better. It's like a law of physics for AI. And what that tells us is that we are nowhere near the ceiling of what AI can do. It's a pretty humbling thought, right? The incredible models we have today are probably the dumbest AIs we will ever have to deal with again. But this nonstop race to scale up, it has a pretty serious dark side. I mean, first off, the environmental cost is just huge. The amount of energy and water these things consume is massive. Then there's the data itself, which has kicked off all these huge legal battles over copyright. They still hallucinate, which is just a nice way of saying they make stuff up, and they can absolutely reflect and even amplify the biases that are already in their training data. And on top of all that, we're just starting to grapple with new security risks, new ways to attack these systems, like tricking a model into bypassing its own safety rules or even hiding malicious behavior. And all of this, it brings us to the final and maybe the most important question of all. Think about it. We started this journey with a simple next word predictor, and now we're looking at complex agents that use tools and are starting to actually act in the world. Figuring out the rules of the road for all this, who gets to use it, how do we make it safe? What are the ethics? That's not just a problem for engineers to solve anymore. It's become one of the biggest societal challenges of our generation.